Okay, let's get started. So last time we were talking about intensity of wave, particularly the intensity of sound. And intensity of sound is how much power passes through a certain area. Okay, so that's power of sound over area, surface area. Power is the energy transferred per unit time. Okay, like if you see a speaker, usually the speakers are rated at 30 watts, 50 watts, right? So those are the powers: 50 watts, 60 watts. How much energy it can transfer per second from one point to another point. That's the power. And intensity is how much power is transferred through an area. Okay, so smaller the area, greater is the intensity. Okay, bigger the area, less is the intensity, because the power has to spread throughout the area. So bigger the area, less is the intensity. So there will be less intensity for bigger area. It's like focusing the sunlight through a magnifying glass. If you focus the sunlight in a small area, you get more intense light. Okay? So next thing is loudness. So the loudness of sound actually comes from the intensity. Okay? More intense the sound, louder the sound is. Okay? Now, we don't use this intensity to describe sound. Okay? So instead of using this intensity, what we use is something called intensity level, or sound intensity level. So we use sound intensity level, which is expressed in logarithmic scale, log scale. Okay? The reason we use log scale is, so for every 10-fold increase in intensity, so these are the intensity of sound. So for every 10-fold increase in intensity, you see the perception of sound increases only by 2 times, doubles. Okay, so if you go from 10 to negative 11 to 10 to negative 10, so there is 10-fold increase in intensity, but the loudness of sound is only doubled. Okay, so when you go from this one to this one, you will hear twice as loud. If you go from here to here, so you are increasing by 100-fold, 100 times. So you're increasing intensity from negative 11 to negative 9, that means times 100. So this times 100 is that. So you will perceive only 3 times as loud. To go 1,000 times, you will perceive the loudness to be 4 times as much. Okay, so this is increasing in the power of 10. Okay, in order of 10. So instead of handling these large numbers, we can just use this this scale, which we call sound intensity level, and the unit for sound intensity level is decibel. Okay, so these are the decibels, and they are logarithmic value of these these numbers. So I'll show you what that means. So that's the sound intensity level, and that's the log base 10 of the intensity. Okay? So this I naught is it's called threshold of intensity. Threshold of intensity is the best level. Okay, best level is the lowest sound we can perceive with our eye, with our ears. Okay, this is the lowest intensity that we can perceive. That's the threshold of hearing. And in order to get the sound intensity level, we take the ratio of intensity to the threshold of hearing. This has a fixed value. Okay, generally all human beings have that as the threshold of hearing. If we go below that, we cannot hear the sound. So that's the threshold. Okay, and then we multiply that by 10 decibel. Now let me show you how we deal with log. So what we do basically, in order to find the log, so you want to find the log of a number. Okay, so you want to find the log of 10. Let's say 10. What you do is you express this as power of 10. So this is in power of 10. It's 10 to 1. Okay, that's 10. And then you take the log 10. So this 10, base 10, and this log, you can cancel that. Okay, this log thing and this base will cancel, and what will be left will be that 1. So the value of log of this is 1. Okay. Likewise, if you want to take the log of 100, you express this as power of 10. So this is 100 is 10 to the power of 2. You can cancel this and that, and then you will have 2. So 2 is the value of that. Likewise, no, this is 1000, so there is a typo here. Fix that. So that's 1000. That's 10,000. So 4000, you have 3 zeros, so 10 to 3, and then you can cancel that and that. You have 3. Okay, so that's how you express all these numbers in logarithmic scale. So this is in logarithmic scale. And the reason again we use this is, this tells us, this matches with our perception of hearing. Okay? So when we go from 10 to intensity of 10, some unit, to 100, the intensity, the level of intensity increases by 2 times. It doubles. Okay, our perception of hearing doubles. So again, I naught is the threshold of hearing. Okay, so we want to know what's the decibel. Okay, what's the intensity of hearing, intensity of sound, at the threshold of hearing. So what we do is, in our previous expression, so we have this expression. So we want to know this intensity of sound or intensity level in terms of log value or decibel unit. So we want to express this in decibel unit. So you plug this in this formula. Okay? So I, for the threshold of hearing, is I naught. So I replace this I by I naught, and that's my get. And then I naught and I naught cancel that. You have 1. Okay. So log of 1. If you punch the number in your calculator, log of 1 is 0. Okay. So beta, or the sound intensity level, is 0. Okay. Or you don't even need to punch the calculator. So 1 means 10 to the 0. You can cancel that and that. Okay. And then you get the value 0 decibel. So 0 decibel is the threshold of hearing. Okay, so this is the question from on your worksheet. Maybe we can. Okay, before we talk about this, let's look at number 3. Okay, from your worksheet. You guys have a worksheet? Okay. No. We need. This again. Anyone needs worksheet? Let's look at number 3. Okay, so we have a loudspeaker 4 meters from where you are standing, and the intensity of the sound at 4 meters from the loudspeaker is given. So 6.2 times 10 to the negative 5 watt per meter square. What is the intensity level at that point? Okay, intensity level. So always think about intensity and intensity level. So intensity is power over area. Okay, that's the intensity. Intensity level is in decibel. So this is the beta, okay, which is 10 decibel log base 10 I over I naught. So this part A is asking intensity level. So this is what it is asking. So you need to plug in the numbers here. 10 decibel log 10. Intensity is 6.2 times 10 to negative 5 watt per meter squared, and I naught is always constant. Okay, so I already show you the value of I naught. That's the value of I naught, which is 1 times 10 to minus 12 watt meter squared. Okay. So you do the calculation. So when you use your calculator, so there are 2 options to use this log. Okay, so you may also you may see log in base of e exponential or log in the base of 10. I want you to use this one, okay, not log to the base of e. So this one is the one you need to use in your calculator. If you choose this one, you get the wrong value. I mean, there is a way to convert from this one to this one. So you need to multiply. Once you get this, you need to multiply by a factor, 2 point something, to get that. Okay? So that's how you do number 3A. And then what is the power emitted by the speaker? So power, now for B, you will use this equation, the first one. Okay? So we want to find P, power. Power is intensity times A. Intensity is given. Okay, so this is given in the question. And then you multiply by area. So area, so when the sound dissipates in air, it goes in 3 dimensions. Okay? So you need to think about a sphere. So sound passes through a sphere like that. So what's the area of a sphere? The area of a sphere is 4 pi r squared. Okay? So radius is from the speaker to the point where someone is standing. Okay? So that's the sphere. And the sound is going in all the directions in addition to this point. So you multiply intensity, given intensity times 4 pi r squared, that gives you the power. So how far should you move from the speaker to reduce the intensity level to modest 15 decibel? So you need to find the distance for that. Okay? So how do you find the distance? Any hint? So let me do number 4, and then I think once I do number 4, you should be able to do part C on this one. Okay. So let's see number 4. So you have two speakers. One has the intensity level of 90, another one has intensity level of 93. Okay? So we want to find the intensity levels, determine the ratio of intensities. So how do we find the ratio of intensities? Now the given value is in decibel, so first we can start with the decibel formula, this formula. This is given, and we need to find that. Okay? That's given, we need to find that. So we have beta for speaker 1 and speaker 2. So we have for speaker 1, that's the sound intensity level, and then that's for the second speaker. So I'm using the subscript 1 for speaker 1 and 2 for speaker 2. Okay, so same formula, but they have different intensities. So I'm writing I1 for speaker 1, I2 for speaker 2, and beta 1 and beta 2. Okay. So whenever you deal with a log, usually it's easier to deal with plus and minus signs rather than multiplication. Okay. So we can subtract B1 minus B1 from B2 or B2 from B1. Okay. So subtract this from that. So B2 minus B1. Okay. So B2 is that. Okay, that's B2, and that's B1. The reason it's easier to deal with negative sign is because of this formula. So if you have log A minus log B, this becomes log A over B. Okay, so that's the rule for log. Likewise, if you have log A plus log B, this becomes log A times B. That's the rule. So the sum of two logs gives log of the product. Okay. So 10 decibel and 10 decibel we have common here, and then this and this. That minus that would be, that goes on the top, okay, and this one goes on the bottom, like using this rule. Okay, log A minus log B is log A over B. So log of that minus log of that is, log of that minus log of that is that over that. And then I naught and I naught is common, so cancel that, and then we'll be left with 10 decibel log I2 over I1. Okay? Now, we are given beta 2 minus beta 1. I mean, we are given beta 2 and beta 1. Beta 2 is 93 and beta 1 is 90. So 93 minus 90 is 3 decibel. Okay, so that's 3. And then on the left we have the expression from there. Now it would be basic algebra. So 3 over 10 is 0.3. Okay, so 3 over 10 is 0.3. And then, how do you get rid of log? we done these kind of things in algebra? Yeah, so you apply exponent, you apply the base on both sides. Okay, if you are dealing with log e to the something, then you apply e, this base, on both sides. Or if you are dealing with base of 10, let's say in this case we are dealing with base of 10. Okay. So this is what we have. So you apply this base on both sides. Okay, so 10, 0.3, 10 log 10. This will cancel. Okay, and then we'll have the desired relationship. So 10 to 0.3, okay, and then here we have I2 over I1. Okay, that's what I have here. So how I got this is applying base 10 on both sides, and base 10 cancels with log 10. So intensity 2 over intensity 1 is 2. So you can do number 3 from the previous question in the same way. Okay, not exactly the same way, but applying the same kind of idea. So I will let you guys figure that out, and if you cannot figure that out, let me know, I can help you with that. Okay. I mean, basically you use let me just give you things for so beta is 10 decibel log 10 I naught. Okay, so this is given. This is 58 decibel. Okay, so this is always fixed. Okay, so using this equation you can find I. Okay, find I, and then once you have I, we have power given. So power is I over A. Okay, so I is 4 pi r squared. Okay, so this is given power of the speaker. This is what you get from here. Okay, and then find this one. Okay, so power is given. Intensity you find from this above equation, and then you find R. That's what you need to do. Okay. Any question?
How did you cancel out the log again?
Which one? This one here?
Yeah.
That's a good question. So usually people have a question about canceling that. So let's say we have some expression x equal to log 10 y. Okay. So let's say I want to write this equation in terms of y. Okay. So what you do is you apply log this base on both sides. So 10 to x, 10 log 10 y. So when you have base log 10, this cancels. These expressions cancel, and this comes to the bottom. So this becomes y 10x. Okay, that's something you learn in math. You do this one. So just apply the base, okay? And then you cancel the base with the log of that same base. This whole thing will be 1. not 10, 1. Does that make sense? No? So I may provide some resources where you can do the review of this kind of math. So I'll post some math review on Blackboard. So please check that, and I think that will give you some review on this. Okay. If you have trouble with that, I mean, you can always use calculator. Although in this one, you may not be able to use calculator. I mean, this is something you need to keep in mind. Okay, so this if you have same base here, then this will be 1, and this goes to the bottom, so this becomes y. We will maybe do some more problems. I will assign some more problems on that, and that will give you some practice. And I'll also post maybe a tutorial or something on this math that will help you to grasp the math concept. Okay, so let's talk about Doppler effect. You might have heard about this Doppler effect in your everyday life. So Doppler effect is basically is the phenomenon where the frequency that you hear, the frequency of sound you hear, changes due to the change in the speed of either the observer or the source of sound. If the observer or the source of sound are in motion related to each other, the frequency of the sound changes. So that's the Doppler effect. Okay? So it's the change in frequency as measured by observer due to the motion of the source or the listener or observer. Now, to explain this phenomenon, we can use this representation. So when a source of sound produces the sound, so this police car is producing some sound, and when it produces sound, it is spread in form of wavefront. We talked about wavefront last time. Okay? Wavefronts are spheres. Okay, so when you produce sound, you produce a sphere. Okay, sphere around you, which is the wavefront, which is the amplitude, which is the crest. Okay, maximum amplitude of the sound, and then in the next instance you produce another one. Okay, you produce this one here. This one goes out, goes out, goes out, goes out, and then in the next instance you produce another one that goes out, produce another one that goes out. Okay, so you're producing wavefronts, and the distance between the two wavefronts is the wavelength. Okay, so we talked about that last time. If you didn't watch the video, you want to watch it again. So the distance between the two wavefronts is wavelength. So that's the one wavelength. That's the one wavelength. That's the one wavelength. That's the one wavelength. And this represents the crest. Crest is where you hear the loudest sound. Okay, the maximum amplitude. If you stand here, you will hear the loudest sound. If you stand here, maybe a little bit less. Okay, less intense. So when the source of sound, so this is the source of sound, when the source of sound and the observers or the listeners are not moving, are not in relative motion, they are all at rest, then wavelength on this side would be exactly the same as the wavelength on this side. Okay, so this gap, you see the gap, they are all equal. Okay, and when the wavelength is same, we have this formula for the relationship between frequency and wavelength. So this is the fundamental relationship between frequency and wavelength. So frequency is speed of sound over wavelength. Okay? So this is wavelength. So frequency is speed of sound over wavelength. So this is the speed of sound, and it's constant for a particular medium. So let's say the medium is air. For air at 20 degrees Celsius, it's 343 meters per second. It's constant. Okay. Now, in this case, because the source and the observers are at rest, so this is also constant. Okay, so we have constant, constant, so this is also constant. So for both these observers, they will hear the same sound. Okay? The pitchness of the sound would be same for Joe as well as Linda. Okay? However, if the source of sound is traveling towards Linda, what happens is, as the source of sound moves towards this person, the wave crests get squeezed, okay, towards the direction where the source of sound is moving. Okay? And this one gets a little bit wider, okay, because it's traveling toward this direction. So this distance would be, wavelength would be shorter than this wavelength. So there is longer wavelength here, and there is shorter wavelength here. And again, it's because of the motion. Okay, so the wavelength gets a little bit squeezed towards the direction of motion, and it becomes a little bit wider where it's leaving. So if you look at this formula, now let's consider Linda. For Linda, now this one is shorter. If this is shorter, so frequency and wavelength are opposite to each other. So if this goes down, this will go up. Okay? So shorter wavelength means higher frequency. Okay? So Linda will hear higher pitched sound than in the previous case. Okay? So the pitchness of sound increases when the source of sound moves towards the observer. Whereas for Joe, so frequency, speed, and wavelength. So for Joe, wavelength increases. Okay, so you see in wavelength here is longer than here, so it increases, and because frequency and wavelength are opposite to each other, inversely proportional, so when this goes up, this goes down. So for Joe, the frequency of sound is less, or he hears low pitch sound, or pitchness of sound decreases as the car goes away from him. Okay? So this kind of phenomena is called Doppler Effect, and you see this all the time in your real life, right? When ambulance approaches you, you hear high-pitched sound. The pitchness of sound increases as it moves towards you. When it's going away from you, you hear the pitchness of sound decreases.
So it's not like the speed of the sound, like you don't hear the sound faster, it's just that
No, the sound remains same. The speed of sound remains same. Only the pitchness or frequency changes. Now, not only the movement of the car affects the pitchness, but the movement of observers would also affect the pitchness. Okay? So for example, here, the source of sound is at rest, okay? Stationary source of sound, and this person is moving towards the source. When the person moves towards the source, this person will hear the frequency to be higher and higher. Okay? The pitchness of sound increases as the person moves towards the source. Likewise, if the person is going away from the source, this source is at rest, if the person is going away from the source, then the person will perceive the decrease in frequency of the sound, or decrease in the pitchness of the sound. Now, we have now 4 different formulas here. Okay, so for the person, this person, towards which the source of sound is moving. Okay, when the source of sound approaches this person, that would be the increase in frequency. That would be the frequency perceived by this person. Okay? So this is the frequency perceived by this person, where Fs is the frequency of the source, actual frequency. Okay? So this is the actual frequency of the source. 1 minus Vs is the speed of sound. Okay, and this V is speed at which source is moving towards this observer. Okay. Now for this person will perceive this frequency. Okay, so minus means there is decrease in frequency. So that's the original frequency. Okay. Original frequency is when the observer as well as the source are at rest. That's 1 plus speed of sound, and then that's the speed with which this is moving away, car is moving away. Okay, so that's the formula when the source is moving and the observers are at rest. Now in the second case, we have this one, when the observer is moving and the source is at rest. So when the observer is moving towards the source, this one gives you the frequency of the sound perceived by this person that is moving at speed okay, speed of observer, and that's the speed of sound. Okay? I didn't use the subscript here, actually I used Vs. Vs is the speed of the sound. And this one, I don't think I need to use, okay, so I don't need to use Vs here. Sorry, in the previous one I used Vs for speed of the, let me go back, let's not be confused with that. Sometimes this subscript can. Okay, so Vs, I use Vs for speed of the source of the wave. Yes. So Vs is the speed of this car, yeah? And then this V is speed of wave. Now in the next instance, this Vs will be VO, the speed of the observer. In this case, it's speed of the source. Vs is the speed of the source. Here in this case, it would be VO, okay? Because now the observer is moving, not the source. Vs is 0. Okay? V is, as before, V is speed of sound. Okay? Now we can combine all these four formulas into one, into this formula. Okay? So this is the frequency perceived by the observer. This is the actual frequency. This is the speed of the observer, speed of sound, speed of source, sound source, and this is again speed of the sound. Now, depending on the motion, you can choose positive and negative sign. Okay, so for example, if the observer is moving towards the source, then we use minus sign in this numerator. Okay? Sorry, plus sign. So the plus sign applies when the observer moves towards the source. Okay? If the observer is moving towards the source, we use plus sign, and we use minus sign if the observer is moving away from the source. Okay? Plus for towards the sound, and minus for moving away from the sound. And when the observer is moving towards the source, this would be 0 because the source is at rest. Right?
You say that again.
Okay, so let me show you a copy and paste on this previous picture. So what I'm talking about is here. So when the observer is moving towards the source, we use plus sign here. Okay? And then this would be 0 because Vs is 0, right? Source is at rest. And then you get 1 plus V naught over V. That would be for this case. Okay? Now if the observer is moving away from the source, we use minus. Okay? Again, for this case, Vs would be 0 because source is at rest. And what you get is 1 minus V naught over V. That would be the formula for that one. Okay? And then I can use the same thing for here. So so in this case, we use minus sign when the source is moving towards the observer. So minus for going towards the observer. Sorry, let me take it back. So in this case, VO would be 0. Okay, this would be 0 because the observer is at rest. So the observers are at rest, so this term would be 0. So you will have 1 on the numerator. This goes to 0, so this is 1. And for the denominator, for the bottom part, when the source is moving towards the observer, you will use negative sign. Okay? And when the source is moving away from the observer, you use plus sign. Okay? So does that make sense? No? So this will tell you what you need to do. Okay, so just read this thing here. So if you read this, that will be clear. So this is for when the source is at rest. This is for when observer is at rest. Okay, in this case, the observer is moving. Okay. In this case, the source is moving. So when the observer is moving, you use this sign rule. When the source is moving, you use this sign rule. And this is just to generalize the 4 formulas, so that you don't have to memorize all the 4 different formulas. Okay. So the next thing is shock waves and sonic boom. Okay, so when the source of sound is at rest, then the wavefronts would have same distance from each other. So in other words, the wavelength on this side will be same as the wavelength on this side. So you spread out uniformly. This is when the source of sound is 0. Sorry, the source of sound is not moving, or the speed of the source of sound is 0. So, source is not moving. Now, when the source is moving to the right, like I showed before, this part will be squeezed. Okay? So the wavelength here would be shorter than the wavelength here. Or in other words, frequency here would be higher than the frequency here. Okay? When this source is traveling to the right. So it produces a wavefront, this big one. Initially it produces the smaller one, it spreads out. And in the next instance, while it's moving to the right, it produces another one, and another one, okay, another one. So it produces the wavefront as it moves to the right. So because it's producing the wavefront as it moves to the right, so the latter wavefronts are shifted to the right. Okay. So this is the first one. So this is the next one because it is produced a little bit later, so it's shifted to the right. This is further shifted to the right. This is further shifted to the right. So this is the case when the object has the speed that is less than the speed of the wave. Okay? So the wave is traveling outward, okay? It's going outward, but the wave is traveling faster than the source. Okay? So the source is traveling to the right, but its speed is slower than the speed of the wave. In other words, the wave is growing faster than the speed of the source, or the red dot. So this is growing faster than the speed of that red dot. And here in this case, the rate at which this is growing is equal to the speed of this red dot. So it produces this wave, and then it produces another wave. So in this case, the wave and the dot are traveling at the same speed. So they all meet at this point. Okay? Because it produces one wave, while the wave is traveling, it's also traveling at the same speed, so it catches at this point, and then next wave produces next wave also catches here. So they all meet on the left side. So this is the case when they both, the spreading of wave and the speed of the source travel at the same speed. Now when the source travels much faster than the wave, okay? So this red dot is traveling faster than the rate at which this is growing. That's why this red dot is in front of the waves. Okay? So before this wave, by the time this wave reaches here, it already crossed the boundary. Okay? Likewise, before this grows, by the time it goes here, it already crossed that boundary. So this is always ahead of, the red dot is always ahead of the circles when the source of the speed of the source is faster. Okay, so what's the consequence of that? So the consequence is when the source travels faster than the wave, it produces something called shock wave. Okay? So all the waves meet at the boundary, and then they add up. Okay, they all add up here and here, and whenever someone is standing in this boundary, the person will hear a big sound, loud sound, which we call sonic boom, okay, which gives a shock wave. Okay, so I think we are out of time. We'll continue this next time. So with that formula, you should be able to do number 5 and 6. Okay, so look at number 5 and 6 and see which formula you need to apply. If you guys have any question?
Okay,
Yes.
on the labs, when are those due and how do you want those turned in?
So labs are usually due one day after the lab. It's due today, but since it's the first lab, you can take a little bit more time. Okay, that's fine. How do you turn in the lab? You turn the lab in using the grade scope. Yeah, so grade scope.
So each person in the group needs to turn in the
Yes.
document. Okay.
Not each person, just one per group.
The writer?
Yeah, so if you guys have time, I can quickly show where Join your. Let me. It will take a minute. Okay.
Because I mean, I've been on Gradescope, I just didn't know.
So let me just.
Is the worksheet through Gradescope as well?
Yes. So everything on Gradescope. Let me. We'll log into that and then show you.
I did extend it.
Okay, so once you log into Gradescope, you will see this, and then you will see all these things, assignments. So for lab 1, you click on lab 1, okay, and then you submit your image here. If it is in PDF, you submit here, okay, upload your PDF. That's all, okay. And if it is worksheet, you click here and then upload your.
And homework?
Yes, homework also here. I will post a link for homework also. So everything on Gradescope.
Okay, so labs are due, so we have labs on Monday, right?
Let's do the due date for lab on Monday.
Labs are due on Wednesday then?
Usually on Wednesdays, but just for this week,
Highlight it.
let's do the due date for lab on next Monday.
Okay, thank you. And we have a lab every single week, right?
Yes.
Okay.
And depending on your role, you need to either be here or at home.
Thank you.
After like the homework and worksheets, do you go over them? Or do you offer feedback on them to know what we did wrong with them?
Yeah, so you will get feedback on the Gradescope.
Okay. Like you'll show us like how to.
Yeah. And then you will also get solutions for the homework.